Good. Okay. You're gonna test the live stream on there. Thanks. You're good. Do you know want to know how to work this? You're, you're listening? Okay. The what? This one? Test. Okay. Yes. It's good. So I'll wait for confirmation.
Okay. Hello, everyone. As people are trickling in, we should have more people coming over the next 15, 20 minutes or so. We're going to get started with some astronomy and AI related trivia led by William Groger.
Okay, so yeah, I'm just gonna ask a couple of questions. The first couple are pure AI questions, then there's some more astro related questions, and then some that are a mix of astro and AI. We'll give you like 30 seconds to think, and then we'll do a show of hands. So, which of the following colleges hosted a workshop that founded artificial intelligence as an academic discipline in 1956? Columbia, MIT, Stanford, or Dartmouth? Okay, who thinks that Columbia created AI? Okay, not very many of you. How about MIT? It's a lot. Stanford and Dartmouth. Okay, it was actually Dartmouth. uh, I put in MIT to confuse you all. Okay, what chess-playing supercomputer beat world champion Garry Kasparov in 1997, marking a major milestone in artificial intelligence? A. AlphaGo, B. Iliac 1, C. Ginsburg, or D. Deep Blue? Okay, who thinks that it's option A, AlphaGo? Okay, option B, Iliac 1, option C, Ginsburg, or option D, Deep Blue? Yeah, it's Deep Blue. AlphaGo plays Go, and Ginsburg is Columbia's supercomputer. Okay. What is the name for the relic radiation from the Big Bang that was discovered by Arno Penzias and Robert Wilson? A. Astronomical radio radiation. B. Gamma ray glow. C. Cosmic microwave background radiation. Or D. The luminiferous ether. Okay. Who thinks it's A? B? C? Okay. Or D? Yep. C is correct, and most of you are correct again. Okay. The Hercules Corona Borealis Great Wall, the largest known structure in the observable universe at 10 billion light years in length, is an example of what type of structure? A. Flux tubes. B. Galactic filament. C. Einstein-Rosen bridge. Or D. String. Okay. Who thinks it's option A. Flux tubes? Okay. Option B. Galactic filaments. Option C. Einstein-Rosen bridges. Or option D. Strings. Okay, it's option B. I think most of you got this correct again. Okay. Machine learning methods will likely be extremely useful in processing the 20 terabytes of data collected each night by what Chilean observatory that is expected to see first light this July? A. Vera C. Rubin. B. Nancy Grace Roman. C, the next generation very large array, or D, habitable worlds? Okay, who thinks it's option A? Option B? Option C? Or option D? Okay, it was actually option A. These are all missions that will have tons of data, but Vera Rubin is the only one that is going to see first light this July and is ground-based in Chile. Okay. The illustrious TNG simulation boxes simulate galaxy formation in large boxes representing parts of the universe. What is the box size by length of the TNG 300 simulation? A, 1 billion light years. B, 1 million light years. C, 50 billion kilometers. Or D, 186 kilometers. Okay, who thinks it's option A, 1 billion light years? Okay, option B, 1 million light years. Option C, 50 billion kilometers. And option D, 186 kilometers. Okay, if you picked, it would be a little bit hard to model a galaxy at 186 kilometers, but it's actually option A. The 300 refers to 300 megaparsecs, so that's why we converted it to light years. Okay. Blanks are machine learning models that predict or mimic the outputs of more computationally expensive models or simulations. A, MCMCs or Markov chain Monte Carlo methods. B, autoencoders. C, surrogate models. Or D, emulators. Okay, who thinks it's option A? How about option B? Option C? Okay, that's a lot of you. Or option D? Okay, this is more even split. It's option D. These are emulators. And I think this is our last question. In 2023, how many papers per month in the top 25 astrophysics journals mentioned machine learning in their title? Is it A, 0 to 10, B, 10 to 20, C, 20 to 30, or D, 30 to 40? Okay, who thinks it's A, 0 to 10? Okay, that's a bit low, but option B, 10 to 20. Option C, 20 to 30. Or option D, 30 to 40. Okay. It was 20 to 30, so it's probably up now though, so yeah. Yeah. All right. Thanks.
Okay. Thank you. Yeah, thank you, Sir William and James Sullivan for writing the trivia and running it. Applause. Okay. And thank you all so much for coming to this event tonight, despite everything that's going on. I realize we're operating under less than ideal conditions. It's probably very annoying just getting into this building tonight. So I'm even more grateful that we have such a large audience tonight. As many of you know, we've been running these events for years. So we really wanted to at least take a stab at holding one of these events, at least one, this semester, to restore some sense of normalcy to our campus and to our neighborhood. So I think it turned out, or hopefully will continue to turn out well tonight. Unfortunately, the chances that campus will be fully open over the next few months are very low. So we're trying to get a bit more creative with how we're running our events. And so I want to talk for a few minutes about some ideas we have for branching out from just these events over the next few months. So the future, question mark, some things we're planning. For one, not too creative, but if you're not weren't too offended by jumping through all the hoops to get here tonight, we are thinking of holding one more event this semester. Same room, Pupin 301, same time, 7 p.m., May 2nd. We don't know yet who the speaker would be, but hopefully soon we'll know that. But without needing to use Columbia's campus, we're also thinking of branching out to other locations. So over the summer, once the weather gets nicer outside and it's warm and sunny, we're thinking of having some events in one or a few of New York City's amazing parks. So these would be public talks, just like we're having tonight, but during the daytime, coupled with solar observing. So looking at the sun, not with our eyes, don't do that, but using special telescopes and special binoculars to see like the hidden structure of the sun. So that should be really fun. I think this will be a really exciting activity. If we can get the logistics right and find the right location, we're also looking to hold some events at local libraries, local branches of the New York Public Library. These would also be like mini talks. Definitely over the summer, we're holding a series of events and activities at a wide array of NYPL locations for children. So if you are interested in this, if you have a young child who might be interested in coming to one of these educational events at these libraries, come talk to us tonight, or you can email us for more information at astro.outreach@gmail.com. That's our email address that's written on the far, well, your right side of the blackboard. Now, I didn't include a panel for stargazing. Unfortunately, we can't stargaze tonight because it's too cloudy, but we are aiming to hold more frequent sidewalk stargazing, where we'll take our portable telescopes out to the streets in Harlem, the Upper West Side, Morningside Heights, maybe even beyond, and observe the moon, the planets, stars, maybe some nebulae, with passersby and hopefully some of you. So for those of you who have been coming here the past few years and are itching to get in some stargazing, we haven't had very much luck on these Friday evenings, but hopefully with these sidewalk stargazing events, we'll be able to actually get in some good observing over the summer and hopefully past that. Yes. And again, for any of these events, before we hold this event, either at a park, a library, on the sidewalk, or in Pupin 301, we'll send out an email blast to our Google group, email group. I know many of you are on there because you use that to register for this event. If you're not on our Google group, come talk to us or send an email to astro.outreach@gmail.com and we'll register you. Also, we have a new website, outreach.astro.columbia.edu. That's too long to write on the board, but if you forget that URL, you can come ask us afterwards. And we have a new Google Calendar on our website that will chart all of our events coming up. So you can add this Google Calendar to your own personal calendar to keep up with when our sidewalk observing is going to happen, when our talks are going to happen, all of that stuff. But yeah, so we are very excited to branch out, hopefully expand to a new audience, or at the very least, a larger, more diverse audience. But for now, we are back in Pupin 301, just as we have been for the past many years, for a very exciting talk from Dr. Matthew Ho on From Data to Discovery, AI's Role in Modern Astronomy. So Matt is a postdoctoral researcher in our astronomy department here at Columbia. He's been here since September 2024. Before that, he got his PhD from Carnegie Mellon in 2022, and then he went to France for 2 years as a postdoc at the Institute of Astronomy in Paris. And as you can probably guess from the title of his talk, Matt is an expert at the interface between artificial intelligence and astronomy. In particular, his research focuses on building machine learning accelerated models for cosmological structure formation and astrophysical inference. In other words, he builds AI models that compute large calculations, run large simulations much faster than would be expected from an ordinary classical computer simulation. Over the past 3 years or so, most of Matt's work has been done under the umbrella of the Simons Collaboration on Learning the Universe, which is an international collaboration dedicated to using AI to better understand the structure and the history of our universe. And very recently, over the past few months, Matt has leveraged his expertise to teach our own department about the applications of machine learning to astronomy. He started up this brand new seminar series that's been very helpful, extremely well run so far. There have been tons of undergrads, grad students, postdocs, even faculty that have attended these seminars. And it's been really great. We're super lucky to have Matt in our department. So all that said, please give Dr. Matthew Ho a very warm welcome.
I think I have this. Should work. Hi, everyone. Can y'all hear me good? Yeah? Okay, cool. I'm pretty loud anyway, so. Thank you all for the very warm welcome. I just want to say this is my first time giving a lecture in this room, and it's extremely nostalgic for me because I am from the New York area, and about 15 years ago, I was part of the science high school program here at Columbia, and I remember being in this room in one of those back seats in the back, taking the entrance exam on these little tiny desks, and I was extremely nervous. And now I'm up here, and I'm still extremely nervous. But not a lot changes, right? Yeah, so today I'm going to be talking about the future of modern astronomy. Everyone has been really excited about AI recently. I'm sure everyone in this audience has at one point heard about the cool things about AI. I'm sure everyone has played with ChatGPT at some point. But really, what I do for my research is try to harness the power of these new tools in defining new ways of understanding our universe, right? So let me catch everyone up. This is everything that has ever happened in all of time on one slide, right? So the universe started at the Big Bang, right? Which was a period of rapid cosmological inflation in which everything was extremely hot and extremely dense and extremely homogeneous. Everything was in the same place at around the same density and at around the same temperature. Eventually, the universe expanded enough and cooled down enough for hydrogen atoms to form, where protons, neutrons, and electrons are able to come together. And then for a long time, the universe was dark. There was nothing producing light in the universe. Photons could travel freely all the way into what we observe today, right? But then all of a sudden, hydrogen conglomerated under gravity and ignited the first stars, which burned extremely hot and extremely bright. Eventually, those stars clumped together and formed new stars and started to form galaxies and planets. And then now we sit here, over here at the right side, at modern day, where we now look back in history, observing all the different galaxies which have formed throughout cosmic history. And we're even starting to see some new physics, like the accelerated expansion of the universe from dark energy, right? Now, I love this plot because it both provides an interesting background to what I'm going to talk about, but also it's a good summary slide for the aspects of machine learning as well, right? So in a much different time scale, machine learning has also developed quite rapidly and provided different effects as it has evolved over time, right? So machine learning, machine learning AI is this fancy term that a lot of you maybe have heard recently, but it's existed for a very long time. Classical statistics and mechanics is technically considered, classical statistics and mathematics is technically considered machine learning, right? We've been doing machine learning for centuries. And it wasn't until recently, upon the development of new machine learning models like neural networks, that it really became efficient to build extremely complex mathematical models, which are really good at learning from data, right? And the first things we started to do with these new models is make existing things that we do faster, right? And that's going to be the first part of my talk. Then we decided, okay, let's start tackling hard problems and see if we make them easier with these new complex models. That's the second part of my talk. And just recently, some new physics has been coming out where we're actually using machine learning models to develop novel discovery that no human has ever come up with before. And hopefully we'll get to that at the end of the talk, okay? But first, unfortunately, before I show you the flashy things, we have to do some math, okay? So now, again, you've all heard of artificial intelligence, probably. Artificial intelligence is a very wide umbrella describing a lot of different things, anything from robots to image recognition on your cell phone, right? But recently, the power of artificial intelligence has been driven by these things called machine learning models, which are simply just mathematical models, which are really good at learning from data. If you can take anything away from the next slide, it's if I show this mathematical model enough examples of data, it will eventually learn how to mimic the behavior of that data, right? So for example, I can show it a bunch of images of blueberry muffins or chihuahuas, right? Which remarkably is quite difficult to disentangle, right? And I can ask the machine learning model to tell me what is the probability that a given image is a chihuahua or a blueberry muffin, right? And eventually, if I showed enough photos of chihuahuas and blueberry muffins, it'll get really good at recognizing the difference, right? And it will be able to assign probabilities like this is a given image is an 87% chance it's a chihuahua, 13% chance it's a blueberry muffin, right? Another example of machine learning is what you might have used before, which is ChatGPT, right? I can ask a question to a machine learning model and then ask it to review literature and give me an informed response. So for example, what is the difference between a chihuahua and a blueberry muffin? Is a sentence I could feed to a machine learning model, and it could give me a table here of the differences between a chihuahua and a blueberry muffin. So for example, this is real. I typed that into ChatGPT. So for example, a chihuahua is alive and barks, and a blueberry muffin is edible and delicious. A chihuahua is covered in, a chihuahua is covered in fur, and a blueberry muffin is covered in sugar. And chihuahua may poop on your rug, and a blueberry muffin may crumb on your plate, right? But it's input and output, right? I feed something to a machine learning model, and then it gives me something on the output, right? And if I show it enough data, it works. But I don't care about chihuahuas and blueberry muffins. What I care about is trying to find the mapping between things that I can observe and things that I want to know about, right? So here's an example in which we train a machine learning model to look at a field of stars and try to predict the distribution of dark matter around those stars, right? And that is important for us because dark matter is dark. It's invisible. We can't see it, right? So if I can train a machine learning model to tell me where the dark matter is, this tells me something about the distribution of matter in our universe, which tells me something about physics, right? And I have just one more slide on this for those who are curious about exactly what's going on under the hood. I won't mention this again for the rest of the talk. People might be curious like how a machine learning model works and stuff like that. It's actually really simple. It's extremely simple. The actual code is difficult, but actually doing it is very simple. And you all, if you've taken high school mathematics, have done machine learning. Linear regression is a form of machine learning. Do you all remember taking a bunch of points and trying to fit a line which captures the relationship between two data points? That's exactly the same thing that's happening with complex neural networks and machine learning models, right? Except instead of 2 parameters, which in this case is slope and intercept, you have thousands to billions of parameters, right? And you can build much more complex nonlinear models with these types of machines. And that's what gives us the power to do these really complex data modeling relationships. Okay? So the first part of my talk, making things faster. You are all going to be my AI, and I'm going to train you with some data, and then you are hopefully going to provide me good predictions. Okay? Thank you. So here are 4 types of galaxies, right? There's many types of galaxies, but here are 4 classic ones. The one on the top left is a spiral galaxy, right? Which is very clear. It looks like a spiral. The one on the bottom left is a barred spiral galaxy, which is similar to a spiral galaxy, but has this long bar in the center, which connects different points. Here's an elliptical galaxy, which basically just looks like a big blob of yellow. These are typically older galaxies, which have outgrown their spiral shapes. And then you have irregular galaxies, which are really wacky shapes and typically don't fit in with the rest of the class. So this is the miscellaneous one, right? And these are very clear images from arguably one of the best telescopes we've ever built, which is the Hubble Space Telescope. Okay? All right. Has everyone looked at these photos and memorized the features? Okay. Let's do some more trivia, right? Okay. This one is a galaxy observed by the Hubble Space Telescope. I want everyone to raise their hands, right? Who thinks that this is a spiral galaxy? Great. Who thinks that this is a barred spiral galaxy? Who thinks that this is an elliptical galaxy? Who thinks that this is an irregular galaxy? Great. It's a spiral galaxy. Are there any AI in the crowd? No? Okay. Spiral galaxy, very clear. Yeah? Okay, let's do one more. This one. Is this a spiral? All right, everyone raise hands. Ready? Is this a spiral galaxy? No? A barred spiral galaxy? Is this an elliptical galaxy? Is this an irregular galaxy? Okay, I got a bunch of you. This is an elliptical galaxy. It looks like, it might look like an irregular galaxy because there's a bunch of foreground dust, which is occluding the galaxy, but the real light is this big blob here, yeah? Okay, you're very good at this. Let's make this harder. Here we go. Yeah? Spiral galaxy, raise your hands. Barred spiral galaxy, raise your hands. Elliptical galaxy, irregular galaxy. Still, very, very good, right? You might notice the image quality declined here, and that's because I'm using a different telescope. Previously, I was using the Hubble Space Telescope to observe these things, which is out in space, right? So it gets very clear pictures. This one I use the Sloan Digital Sky Survey, which is based on land, right? So it's getting harder, no? Okay. If you think you're all so smart, let's figure this one out, okay? Spiral galaxy, barred spiral galaxy, elliptical galaxy, irregular galaxy. Okay. So to be honest, we don't know, right? The machine learning models are telling us that this is a barred spiral galaxy, but we can't go out there and measure it, right? Good job to those who guessed that, right? So this is one use of machine learning models in astronomy, right? There's this collaboration of scientists called the Galaxy Zoo collaboration. And what they've done is they've built a website in which citizen scientists like yourselves can go in and hand classify different galaxies on the sky, right? So basically what that does is that associates images of galaxies with classifications of galaxies. And then what we can do is use this data to train machine learning models to do exactly what the humans are doing, which is to look at a galaxy image and then classify whether or not it's an elliptical galaxy or a spiral galaxy or an irregular galaxy. And this collaboration has been going for like 10 years now. It's been going for a very long time. But just recently, if you guys have paid attention to the news, the JWST telescope launched. And just, I think, a month ago, they released photos, new galaxies on this Galaxy Zoo website from the JWST telescope for the very first time. And there's a ton of galaxies. So if you go to this webpage or you just Google Galaxy Zoo, you can go and start to hand classify some of these galaxies to help citizen science. And in fact, some of the galaxies you'll find on that website, you will be the first people to hand look at them, right? Because there's so many galaxies. Us astronomers are not sitting down and doing all of them, right? We need people like you, right? So this is where we get data to train machine learning models to do these things, okay? Now, you're all very good at that task. I'm going to give you another one, right? Okay, so somewhere in this image is a strong gravitational lens, right? A strong gravitational lens looks like this. This is a high resolution photo from Hubble. And what happens is light from distant galaxies feel the effects of gravity of a foreground object, like a very heavy galaxy. And then when we observe it here on Earth, the light looks bent around this central object. So in this case, there's a very high massive galaxy here, and the gravity is so strong that it's bending the light from this background galaxy. Okay, now one of these systems exists in this image. Does anyone see it? There's a in the hoodie right there. Okay, why don't you tell me left or right? Left. Right here. There you go. Good job. We found it. You might be AI. So this is another example, right? Instead of us staring at these, us astronomers staring at these images for hours and hours trying to find these systems, it makes a lot more sense to train a machine learning model to identify where in this big field, where in this big field of images these things are. And both this system and the previous system that I just described are actively in use. These big major telescopes that are trying to discover these objects are actively using machine learning models to try to identify where these systems are, right? This is making things faster, right? This saves us time, right? Instead of having a graduate student for hours and hours try to find these things, instead we can ask a machine learning model to do so, okay? Now, let's step it up one more notch. This is 10% of the galaxies observed by the Sloan Digital Sky Survey, right? Here's Earth, this little blue dot here, or actually this is kind of our Milky Way, right? It's an extremely zoomed out photo, right? These are real galaxies that were observed by the Sloan Digital Sky Survey. And this gray box here is about 5 billion light years in size, right? And there's a ton of data in this image, right? Every single galaxy has a position, it has a color, it has a redshift, it has a type, right? So how do we parse all this data, right? So let me ask you, my highly trained AI, where in this image is the dark matter? Yeah? I saw a hand raise. Do you want to guess? The yellow thing here? I mean, it could be. It could entirely be. I don't know. You know better than I do, if anything. The thing is, we deal with so much data, and this data is extremely unstructured and extremely complex. It's not just images. Images are easy, right? When we're dealing with all this data, all these galaxies which are distributed on the sky, it's extremely difficult to extract information which is relevant for us to describe, what is dark matter? How much is there? Is there dark energy effectively, right? So that leads me to my next point, making things easier, okay? So recently, in the past 5 years, there's been a new philosophy about using machine learning in astronomy, right? So this is classical computational astrophysics, right? Which is that we've been trying for decades to build a simulator of the universe, right? This simulator has every aspect of physics that has ever been written down built into one huge code, right? And there's many codes, there's many versions of this, right? But this has been our goal, right? To incorporate everything that we know about inflation and the Big Bang, to incorporate everything that we know about dark matter and dark energy, to include everything we know about galaxy formation, about black holes, about how stars evolve, and then evolve that with gravity and hydrodynamics to produce images which look like our real universe, right? That's been our goal, okay? And so let me give you an example of that. Here are 4 simulations, each implementing a different version of this universe simulator, right? What you're seeing is them at the very beginning of the universe slowly evolve into present day, right? Here are 4 different simulations, yeah? And what you start to see is the matter starts to clump together, yeah? You start to see clusters forming. You start to see filaments forming. Each of these little blue dots is a galaxy, yeah? And then you start to see the galaxies start to emit radiation, right? They start to blow gas out into the interstellar universe. I mean, the intergalactic medium, right? And it's an extremely complex, extremely heavy simulation that takes millions of CPU hours to run. Yeah? But we can do it. In theory, we can do it. Okay? So again, this is what we're thinking about. When I talk about a simulation of the universe, it's literally we're going from the beginning of the universe to the end, putting in all the laws of gravity that we know, all the information about dark matter we know, all the things about galaxies that we know. And then our goal for observational astronomy is to turn this arrow back around, right? Is to say, if we observe some data on the sky, what possible models of galaxies would be consistent with that data? Yeah. Which of our simulations looks like the real universe, right? Or which of our simulations has the right models of dark matter and dark energy, which mimic the effects that we see in the real observations, right? So in theory, I could run infinite numbers of simulations and find exactly the right one, which put galaxies in exactly the right place, which produce stars in exactly the right color, that would give me exactly the right model for physics that I need, right? This has been the philosophy, right? If we can simulate it, then we can infer it, right? The challenge is, of course, I don't have infinite computation time. I can't run infinite numbers of simulations, right? So how do we get around that? And that's what I'm using machine learning for, is to do this problem here, which initially was thought impossible, in a much easier way, okay? So let me give you an example. So here's an example simulation in which we model the evolution of matter in the universe all the way from the Big Bang 13 billion years ago to present day observations, the present day distribution of galaxies. And then we apply all the noise, selection, and telescope effects that we would expect to see using the Hubble Space Telescope or using the Sloan Digital Sky Survey, right? So we have a simulator, which takes us from the beginning of the universe to the observations we see on the sky, okay? And then I take that simulator and I run it thousands and thousands of times, right? Which gives me thousands and thousands of pairs of the initial state of the universe and the final state of the universe, right? So I have a simulator which brings me from 13 billion years ago to present day, right? And then what I do is I ask a machine learning model, just like the photos of chihuahuas and blueberries, to intake an observation at present day and tell me what is the distribution of matter at the beginning of the universe, right? So I'm turning the clock backwards. I'm running physics backwards. I'm observing modern day, and I'm asking it to tell me where was all the matter 13 billion years ago, okay? And so I can do that. Let's assume I can do that. Let's assume I can run all those simulations. Let's assume I can train that machine learning model. And then what I can do is I can take these observations that I showed you previously, these distributions of galaxies on the sky, and I can ask my machine learning model, okay, given this distribution of galaxies in modern day, what is the distribution of matter that could possibly give rise to that distribution of galaxies, right? And so now I have all of these possible universes 13 billion years ago, and I know exactly where all the matter could have been 13 billion years ago. And you might say, okay, Matt, why is that useful? Why do I care what was happening 13 billion years ago? That doesn't tell me anything about physics. But check this out, okay? So what I can do is I can take each of these realizations of the beginning of the universe and then run my simulation back forward in time, right? I can assume I sit in my real universe and I watch the evolution of our universe as it evolves with time, right? So now check this out. Here are two simulations, exactly as I described them previously, right? Where I took a constrained realization of where the matter was 13 billion years ago, and then I ran a very high resolution simulation to model what is happening in our local region of the universe, right? Okay, so let me play this video again because I was talking during it. So what's happening is, the universe starts all homogeneous and flat, and then slowly you start to see the gathering of material through the forces of gravity, which end up forming two bright spots just near where we exist in the universe, right? So we exist at the center of each of these images, right? And the final result of these simulations with these constrained initial conditions of the universe is two bright galaxies which sit where we are sitting. Does anyone recognize those two? Yeah. Yes. Nice. You got it. So that was actually the formation of the modern day Milky Way, right? What we can do with machine learning is we can do this extremely complicated relationship between all of this data to tell us where was the matter 13 billion years ago, and then I can run a really complicated simulation to show me exactly where we are in the universe, what matter fell into our galaxy throughout the course of its life, and what matter makes us up today. Yeah? So I was going to say there's Milky Way and M31. What is M31? And then Andromeda Galaxy, but you already got it. So good job. Okay. I think that's incredibly cool. Right? Now, what's even cooler is this. So, we talked about making monotonous things faster. We talked about making hard things easy, right? But what machine learning has so far not been able to do is push us further in scientific knowledge, has been able to come up with things that we have not been able to come up with yet, right? And what I'm talking about here is discovery, right? How can I ask a machine learning model to discover something new? Okay, so first off, what is discovery, right? Very famously, Isaac Newton discovered the laws of gravity by watching the orbits of our local planets around the sun, right? Basically, he said the only way that planets could orbit in an elliptical orbit, the only way that we could observe some retrograde features of the path of Mercury along the line of sight is that there must be some physical force which is causing the planets to stay in orbit, and the shape of that physical force has to be 1 over r squared, right? Where r here is the distance between any 2 points, between any 2 masses, yeah? And to be honest, Isaac Newton was a brilliant person, right? But he was just looking for a formula that worked, right? He didn't know. Like, there weren't no first principles things which led him to just this discovery. He was trying out different forms of equations until one of them produced the elliptical orbits that we see today. Yeah? We can do the same thing with machine learning. So here's an example of a really cool paper from 2022 in which the authors modeled the orbit of the sun, the Earth, and all the planets and all of their moons using a machine learning model. So basically what they did was they tracked the orbits of, in this case, the sun, Venus, and the Earth, right? And they tracked them as a function of time, right? So here on the left is early times, here on the right is late time. And what you can see is the orbit of the sun, the sun stays in the same place, so it doesn't really move through time. But Earth and Venus are constantly orbiting around the sun, yeah? And then they asked, okay, can you come up with a functional form for a force which would cause this behavior? They didn't tell it anything about gravity. They didn't tell it anything about physics. All they said was, if you had an interaction between each of these different planets, what could cause this? And they used this machine learning model, which is called symbolic regression, which searches through all possible patterns of equations, right? So what it's doing here is creating this equation over here, right? And it's looking for an equation which fits this curve, right? And it's constantly adding different pluses and minus signs and divides and cosines and sines until it comes up with something that works. Yeah? What do you think it came up with? That, right? So after a lot of training, and to be honest, it took some tweaking to get it to work perfectly, they came up with an explanation for these orbits, which used this functional form here, right? And remarkably, it's exactly the same force as for gravity, right? You see, it's some constant g, some constant c, times the mass of one body times the mass of two body divided by r squared And the mass of one body, mass of two bodies divided by r squared. And then this term over here kind of defines the fact that this is just a force in the x direction. So really these two things cancel out. And then this is the final function form. Yeah? Cool, right? Very cool. From nothing, from absolutely nothing, only information about the orbits, exactly like Isaac Newton, it came up with a form that worked. Okay? Now, you might say, Matt, that's boring. We already know gravity. What's the point, right? Does anyone recognize this map? Great Britain, Italy. I've gotten Westeros before. No. So I blacked out a bunch of the names here, right, to make it not obvious. This is not a map of Italy. This is not a map of Great Britain. This is not a map of Westeros. This is a map of all of astronomy, right? So let me explain. Just give me a second, right? Okay, so Karthik Iyer, who's a postdoc upstairs here at Columbia, took a pre-trained model like ChatGPT, a large language model, and fed it every paper that has ever been written on astronomy, right? To try to understand what's going on, right? And then it basically allowed it to create this app here, which is called Pathfinder, which if you're interested, you can take a photo of this QR code. It'll bring you to this website. And what this app does is you can ask it an astronomy question, and it knows the answer to that astronomy question, right? So for example, it's hard to read all this stuff, but for example, in this, what they asked it here is what is the expansion rate of the universe? And what it did was it searched all of the papers that it has access to and came up with a consensus answer which described what is the rate of expansion of the universe. Yeah. And so now if you go on your phone, and to be honest, I haven't tested this in a while, so it may or may not work. We'll see. You can actually see, you can ask it a question like, what is the biggest planet in the universe? What is the biggest star in the universe? What is dark matter? What is dark energy? And it will come up with an answer. It might not be the correct answer, but it's based on previously written astronomy papers. And now what this is what Karthik has done as he's taken apart the machine learning model. He's taken apart ChatGPT and looked at what it's learning, right? And this is a cartoonified map of the relationships between different astronomy topics, right? So automatically, right, without any manual input, he just threw astronomy papers at it. This ChatGPT thing could figure out that dark matter and dark energy are related, and therefore they're very close together. These are both theoretical models for cosmology. Yeah, it could figure out that galaxy clusters and galaxy formation are very close to each other, and that galaxy formation is really dependent on black hole seeding, right? Because every galaxy has a black hole in the center of it. Yeah. It clumped together all of these extremely small compact objects like neutron stars, like pulsars, like supernovae. These are all single stars that have kind of formed into one compact object, right? And are distinct from the larger galaxies. Yeah. So all of a sudden, from nothing, information is starting to be gathered, and you can start to learn about the relationships between different things, which I find absolutely astonishing. Okay, and now what is quite possibly my favorite paper of the past month is this one here. So this paper literally came out 3 weeks ago, and what it is they took ChatGPT, DeepSeek, and Llama, these famous large language models, which you might have used at home, and they asked it a bunch of astronomy and physics exam questions, right? It's called the Theoretical Physics Benchmark, and if you want, you can go to this website and look at all their results. So this is a question here in cosmology, so it's an aspect of astronomy, in which they asked it a very complicated question. We don't have to get into it, but basically what it is, it's like, given some dark matter field, if I populate that dark matter field with galaxies, what is the eventual thing that you would measure on the sky, right? And what it did was it did a whole lot of math, right, written in LaTeX, and it talked about understanding exactly what the problem is asking. It talked about solving integrals necessary to do that. It talked about finding a final symbolic expression, and then it wrote Python code. It wrote computer code to solve the problem for you, right? And the insane part is that it's right, right? An expert came in and without any knowledge of what the solution to the machine learning came up with, came in and wrote their own answer. And both the machine learning model and the expert came to the same answer, which is crazy, right? And what's even more astonishing are these statistics here, which might be a little bit hard to read if you're far back, right? This is difficulty of problem on the x-axis versus accuracy of solution on the y-axis, right? So these first bars represent easy undergraduate level problems. These ones represent regular undergraduate level problems. These ones represent easy graduate level problems. These ones represent hard graduate level problems. These ones represent like full research scientist level difficult problems. And the crazy thing is that if ChatGPT took an introductory graduate level course, it would get an 87% on the exam, right? 87% of the questions it got right, right? Is that making any of the graduate students in this room nervous? Yeah. Which is remarkable, right? It's coming up with physical insight that has never seen before, right? And is able to understand mathematical proofs sufficiently enough to come up with a very complicated solution, right? Okay. So I'm going to finish this off with a summary, right? Here are all the major astronomical discoveries made by AI in the past 10 years. There are none, right? So this is the grain of salt that I want to present this information to you about, which is that this is an extremely powerful technology, and we're just now at the brink of being able to use it to its full potential, right? However, it's extremely new. We still don't understand what it's doing, and we still don't know how to validate it sufficiently enough to convince the scientific community that these are useful information. For it to be a major discovery, everyone in the community has to accept it, yeah? And so we're not there yet. We will be there soon, and maybe some people who are sitting in this audience who are younger can contribute to that development. But we're not there yet. But it's an extremely exciting time to be in this field. I personally love it. So with that, I'm just going to conclude. Here are my summaries that AI is just a tool to accelerate our scientific exploration. We are actively using AI and machine learning to use in astronomical surveys. We can now test physical theories to an unprecedented precision. And AI is now starting to produce novel hypotheses, but we have yet to widely accept all of its discoveries. And I'm going to put my email here if you have any questions, but I'm also happy to take questions now. Thank you very much. Okay, any questions? Yeah. Yeah, so I actually excluded this from the talk because I thought it would be too technical. These are all the different redshifts of each of the galaxies. So redshift is basically equivalent or very similar to a distance metric, right? Because what redshift is the frequency of the light that's emitted by the galaxies is shifted because it's moving away from us. Just like when an ambulance drives by you, it'll start a very high pitch and go like wee woo, wee woo, wee woo, wee woo as it goes past you, right? The same thing is happening with these galaxies. And because the universe is expanding, the further something is away from us, the faster it's moving away from us, and therefore the higher the redshift is. So it's like a very, it's a very technical thing, but that's what the color means. Right there, yeah. That's an interesting question. So except for like the ones that read papers, none of the other models were LLMs. They were all classical neural networks. LLMs have only been a thing for the past 3 years. I actually have a colleague who is using LLMs to, large language model, ChatGPT, right? So it's a very specific neural architecture. It's a very specific machine learning model, which is used to process text data. So some people have been using it for like things like the galaxy distribution on the sky. in which instead of words, they are representing space by token. So they're representing basically each position in space with a different word, right? And in much the same way that you feed, X, Y, Z positions to a regular neural network, you can feed X, Y, Z words to a large language model. And it's actually working quite well, but that's literally the past 6 months we've been doing that. So, other questions?
I'm going to interrupt real quick.
Yeah, go for it.
With 2 points. Well, actually 3 points. One, fantastic talk. That was amazing.
Thanks.
Okay. The second point is, if you want to ask a question anonymously, you can use this Google form or the QR code. It'll show up on my laptop, and every 3 or so in-person questions, I'll ask Matt one of the online questions. Last point is we're also going to do a raffle. I guess we're going to give away 3 amazing pieces of Columbia Astro merchandise, 4 amazing pieces of Columbia Astro merchandise. Jen has thrown in a 4th one for extra special. So if everybody here was registered to get onto campus, so I'll be drawing from that registration form. And I guess every 5 or so questions, we'll just pull a thing.
Okay.
So yeah, we can get back to questions now.
Should we still take hands, or should we do this?
Yeah, we can alternate between hands and online stuff.
We'll start with a hand one, then we'll go. So we're here. Yes.
What was it that specifically made our galaxy and Andromeda as opposed to just a simulation that ended up with 2 clumps? And how far back are you going? Are you going back 13 billion years? Or what was the
Yeah, so you're exactly right. There are lots of possible simulations that could end up with 2 clumps next to each other. The thing that made that one special is that we know that that is exactly how Milky Way formed. That's exactly how Andromeda formed. And the reason we know that is because we inferred where the matter was roughly 13 billion years ago. I think actually that one might have been around 10 billion years ago. But we fed the machine learning model a present day observation, and then we asked it to tell us where the matter was 10 billion years ago. And it just got really good at doing that. And then eventually, we applied it to real data instead of our simulation. And then we took the results from that application to real data, and then we fed it into another simulation, which produced those images that you saw there. So you're right to be skeptical that that might not be the exact formation of our Milky Way and Andromeda. And in fact, there could be many groups of galaxies that look very similar to that. But we think that's how those 2 things form.
From about 10 years?
Yeah, starting from 10 billion years back, evolving all the way to present day. So in the red shirt there, yeah. Mm-hmm. That's an excellent question. That's kind of my job, right? So what we've been doing for the past 5 or 6 years has been I'm just going to assume one model, right? I'm going to use one neural network. I'm going to use one machine learning model, and then I'm just going to see how well it does at the end. But really, you can choose any different type of machine learning model, and it would do a similar job. So which one is the best? It's really hard to tell. So my job is coming up with ways to discern which one is best. Ultimately, what we do is we train a bunch of machine learning models in parallel, and then we evaluate them on the same data. We evaluate them on apples to apples. It's kind of like you might have 100 students in a class. They all take the same test. And whichever one does the best, that's the one that we apply to real observation. That's kind of how we do it. But it's still a very new field. So we actually don't have an agreed upon method of doing it. Yeah. You had your hand up. Go ahead. Yeah.
What about there's a debate about the Hubble constant and some the conclusion based on type 1a supernova different observation of cosmic magnetic background. And you mentioned in one of the slides that if you ask the acceleration rate of the universe for AI, it gives you a definite answer. So is this debate concluded yet? Or if not, do you think AI can?
That's an excellent question. So for context, there's been a huge problem in cosmology with a disagreement on how fast the universe is expanding. Some people think it's very fast, some people think it's not so fast, right? And using different observations, they've come to different conclusions. And what this person asked was whether or not the machine learning model, if I asked it that question, how fast is the universe expanding, will it come up with an answer? You actually might notice, I don't know if we can pull up the slides. Can I show that one? If not, it's okay. Okay. Okay, it's fine. I can just explain it. Okay, basically what that slide said is there was a moderate consensus on the answer to the question that was asked, which means that the astronomy literature was not in full consensus. So the machine learning model was like, I don't actually know. I'm not going to pretend to know. I'm just going to tell you what the astronomy literature said. So no, it would not be able to solve that by itself. Yeah. Oh, I can show it then. It's right here. Yeah, so right here, consensus, moderate agreement, right? So we're not exactly sure what it is. Okay, other questions? Yeah.
Yeah, when you've been able to focus in on a single model that kind of shows how the universe or parts of it are evolving and you feel like it's right, is that also then predictive? And are you able to make new kind of discoveries as to the future of the universe?
Yeah, we're trying. So one such example, right, is instead of running a simulation, I can simply train a machine learning model to emulate the simulation, right? So to make a fake version of the simulation. And then I can ask the machine learning model, what information did it use to make a fake version of that simulation? And maybe that will tell me something new about physics. We are trying that, but the problem is that machine learning models are black boxes to some extent. They're really hard to figure out what they're thinking. And so there's been a lot of people working on that, trying to pull apart the machine learning model and figure out what it's doing. And to some extent, this is an example of that. But it's very hard. So that is an excellent insight in that we want to go down that route, but there are no positive results yet. Yeah, right there.
Yeah. I'm sorry.
Yeah.
Well, first, okay. So, a question from the YouTube live stream. Matt, can you repeat the questions when people ask them?
Oh,
Please?
yes. Sorry.
Thanks. Oh, no worries. Then, okay, I'm going to ask one question on the sheet, and then we're going to do the first raffle. The first question was, so what is the general method of how astronomy and also AI are used in aerospace engineering, mainly for designing control systems, satellites, and rovers?
So I know that I'm not an expert on aerospace engineering, but I know one very strong use case of AI is in turbulence modeling. So, have you ever seen like a wind tunnel with like an airplane wing in the wind tunnel, and then you see the smoke going over the airplane wing and then kind of flowing out to laminar flow behind it? You can simulate that. You can run a simulation with fluid dynamics models to simulate that, but it's really hard and it's really numerically intensive. So what people are using AI for is to make that faster so that they can really investigate all possible designs of airplanes to find the ones that are the most, let's say, drag resistant, that kind of thing.
Great. Okay. And Jen, what is our first merge? Okay. Okay. Fantastic.
Oh, I think I can turn mine off.
No, we're good. Okay. Yeah, it's a Columbia Astronomy themed mug with our rooftop observatory on there as a cartoon. And is Catherine Zhu here? Oh, fantastic. Great. Okay, and I guess we can go back to in-person questions, and then after like third question.
Sure. Go ahead.
I mean, I guess this is kind of more of a speculative question, but where you mentioned near the end about like, we aren't yet at the point of like AI making sort of new discoveries. I guess sort of, I guess looking into the future,
next few years, where, like, what areas, I guess, do you, I guess, personally expect to see, sort of, I guess.
Yep.
I'm not an
Mhm.
astrophysics person, so I might not know the terminology, but
Mhm.
I guess sort of AI, making a testable, prediction or something like that actually gets, confirmed.
Yeah. So the question was, we have yet to make any major discoveries. Where do we see AI being the most helpful in making new discoveries? Like what fields, right? So first I'll say humans will always be in the loop, right? At least until we have, robot assistants. No one's going to go out and design, AI is not going to go and design a telescope and go build it in Chile by itself, right? So baseline, there will always be humans in the loop. And also baseline, like we cannot do astronomy without physical intuition, right? The whole point of observing stuff on the sky is to say, I'm going to think about something based on my understanding of my local universe, and I'm going to try to project those laws from my local universe into the sky, right? So there needs to be some aspect of a mental, like human mental intuition, which produces that understanding. And then we can use AI to go test those tools. Now, it's possible AI will be useful in what's called hypothesis generation, which is like maybe humans haven't thought of something yet, and it will suggest something, and then that will spark intuition in humans, and then they'll go and dig into the data and figure it out for themselves. However, there will always, in my personal understanding, is there will always be a human in the loop. And we'll get rid of a lot of the monotonous, simple tasks using AI, but our physical understanding will still need to be there. Back there, yeah, go ahead. So one thing, for example, is we know that eventually Andromeda is going to collide with the Milky Way. We definitely know that. They're currently hurtling towards each other by gravity, and there's nothing that's going to stop them. Like billions of years in the future, we're not exactly sure. So a big debate that's been going on for the past 10, 20 years is what is dark energy and what is the behavior of dark energy? Because what it seems to be doing is accelerating the expansion of the universe. And depending on exactly how much dark energy there is in the universe could rip to shreds, and then everything will be empty and dusty, and there will be absolutely, like, there will be no more galaxies, there will be no more stars, everything will be empty, right? Or if there's not enough dark energy, then eventually gravity will overcome things and everything will collapse together. And then there will be another big bang, like everything will get hot and dense and gravity filled, and then it would collapse into a single point. We don't know. We don't know the answer to that. And so as a result, we don't know, our simulations also don't know. So great question. I would love to know the answer, but fortunately I don't have a good one. Yeah. Right here. Yeah, so when all the galaxies will collide, will there be another Big Bang? Yeah, I mean, if dark energy is not strong, we don't know what dark energy is. There's some energy out there that we don't know what it is. If it's not strong enough, then eventually all the galaxies will collide, and there may be another Big Bang after that. Yeah. Go ahead.
Now, LLMs are not deterministic. I think for the machine learning models we use there is the same, like with the training, the weights, and the backward propagation. So we can run the same simulation you had with Andromeda and with Milky Way over 10 billion years. If you train this again, run this again, that's completely different, or you always get the same result.
Yeah. So the question was, right. The question is, there are some. So large language models are an example of a machine learning model that doesn't always give the same output if you give it the same input. If you ask ChatGPT a question twice, it'll give you two different answers, right? Or two slightly different answers. That we are building models that do that as well, right? Because, for example, when I showed this here, right? This one here, right? Oops. When I showed this one, I'm not telling you that there exists one exact distribution of matter 13 billion years ago. I'm telling you that any one of these possible realizations could have been the universe 13 billion years ago. So we are inherently building in, randomness into our machine learning models to capture what we don't know, to capture our uncertainty. So this is something that's only developed over the past 5 years-ish. It's something I work on as well, but yeah. Go ahead.
Another online question and then another raffle. So the second online question was, how much training data was used for the model that predicts the location of dark matter?
Question was how much training data was used for which model?
That as predicts the location of dark matter. I guess maybe they're referring to the.
Yes. About 2,000 simulations. So we did 2,000 simulations of the universe. And we did some fancy things where we flipped the universe, so we didn't have to run another simulation upside down, that kind of thing, to make it seem like more data. But yeah, about 2,000 examples. Yeah.
Perfect. Okay, and then for the raffle, what's the next piece of merch? Tote bag with our rooftop observatory on it. Very cool. And this is going to, is Aditya Jain in the room? Okay, I will reshuffle. Oh, 1 second. Okay, is Wenkei Lee? Oh.
Okay, are there any questions? I want to favor, there's a young man in a hat in the back. Yeah. Were you stretching or were you asking a question? Okay. Go for it. Yeah.
For things that can be how can that ever be verified by you, right? Because then don't we each have like our personal models that we have a bias towards that we believe is the correct model, but there's no actual way of proving what the right model is, and the only way to achieve the simulation and the simulation itself.
Yeah. Yeah, that's actually a great question. So the question was, if the only way we can get this information from the sky is to use black box machine learning models, how do we know it's the right model? / maybe how do we trust that that information is useful, right? Or it's valid, or is it verifiable? I think so. This is a very hot topic in the community. In fact, a lot of the older faculty on my faculty review panels don't want to trust machine learning. It's entirely fair, right? Like, because classically, physics has been done a very specific way where you take a notepad and a pen and you figure out some analytical derivation and you try to extract information. So what we can do is we can show that our machine learning models behave exactly like our simulations. We can show that. We can run more simulations. We can keep testing, we can keep giving our machine learning models tests to evaluate. And if it keeps hitting 100% on every single one, then we know that it's doing well on simulations. But we can never go out and measure, let's say, the mass of Andromeda to know that it's predicting the right mass when we try to go measure it. So you're right. There is this uncertainty about trusting machine learning models. All we can do is say, if I trust my simulations, then my simulations can be used to constrain my machine learning models, which can be used to apply to observations. So that's all we can do. And unfortunately, you do have to make that leap of faith to say that my simulations are correct. And that's a very hard thing to do as well. So it's a very hot topic. It's a very great question. But ultimately, it is kind of a different philosophical view of astronomy. Yes. Yeah, the quality of the model is only as good as the quality of your training data. Yes. You've had your hand up for a long time. Yeah.
So how do you trust that data? Because it could be a high school student.
Yeah.
Apparently, the quality depends on the data.
Yeah. Yeah. Right. So the question was, if our machine learning models are only as good as our training data, and in the Galaxy Zoo example, we were asking citizen scientists to create the data. How do I know that's trustworthy? Because it could be done by a high school student or it could be done by a senior professor. What they did in that project was the real astronomers went and labeled some of the data. And then they sought to find whether or not the ones labeled by citizens were the same as that of the expert astronomers. And in that case, they actually found like 99% of the time, the citizens were doing it well enough. So in that example, it's fairly trustworthy, but we have to do these validation tests every single time we do this to make sure it's okay. Right. So the problem is, if an AI has never seen a galaxy before, let's say that, it's not going to know the difference between a spiral or an elliptical galaxy. So there has to be some baseline training. And the other problem is when you switch to a different telescope, the problems with your observations are different, right? You notice when I went from the Hubble photo to the SDSS photo to the JWST photo, the quality of the image changed. And that's going to totally throw a machine learning model off. I mean, it'll do okay. Yes. Somehow humans are very good at adapting to new types of data. Yeah. So our machine learning models are not as good as humans yet. Yeah. We still trust humans. Yeah. Absolutely. Yes.
Oh,
So just building on the point that your models are only as good as the input data. Now that we have these new techniques, does it change perhaps the kinds of telescopes we want to build in the future or what we want to do with them?
Yeah, absolutely. So machine learning has only been popular for about 10 years, and it takes about 30 years to design and build a telescope. So we are starting to think about how to build telescopes to optimally retrieve data that machine learning models would be really good at. But the problem with that is, if the telescope is not going to be ready for 30 years, we don't know what machine learning models will be available in 30 years. So we can try to make a guess to design it around our existing machine learning models and hope that they get better in the future. And in fact, some people are starting to do that. But ultimately, the pace of this is just so fast that we have no idea what's going to happen by the time we build the telescope. Yeah, but then, so there must be a model that you can build to see what telescope it might do. But yeah, I mean, then you have to deal with like human sociology, which is like that's an even challenger problem than this, right?
okay, so we have two more questions online. So I'm going to do these and then wrap up the last two raffle items too. And then I think we should try to wrap up the questions, but you should absolutely feel free to come down afterwards and ask Matt as much as you want, or as much as he wants. So the second to last question is, where can someone in data science get involved with improving AI for astronomy discovery?
That's a great question. So you can do, so if you're involved in data science, you're interested in getting involved with astronomy, the baseline thing you can do is go to Galaxy Zoo, right? Go to these citizen science websites and contribute training data. But if you have skills in data science, all of this data is public. All of this data is like, astronomy is great because there's no sociological problems with releasing astronomy data, right? As opposed to other types of data. So most of this data is public. You can go and find these simulations that I just referenced on the internet. All you have to do is Google these papers, and they often have links to this data. So if you want to go in as a data scientist and play with this data and see what models you use, and then maybe email me and we'll write a paper together, we can do that. Right.
Perfect. Okay, and we're giving away another mug, and then after that we'll give away another tote bag. But is Delina or Raidu in the room? Oh, perfect. The last online question. What programs and tools were used to produce the images and simulations that you showed? Did you collaborate with computing facilities?
So the last bit of that question?
Did you collaborate with computing facilities?
Yeah, absolutely. So all of this stuff is run on supercomputers. So I can't run this on my Mac, right? My Mac is not sufficient to do this. We have supercomputers here at Columbia. I use a supercomputer in Indiana at Purdue. I use a supercomputer in Pittsburgh. So all this data is hosted all over the world. I use a supercomputer in Paris because I was in Paris for 2 years. So all this data is all over the world. And you really need like tons of CPUs, tons of GPUs to do this analysis. And yeah, so yeah, you have to have a supercomputer to do a lot of this stuff. You want to take one more, or
Okay, well, the last raffle, the last tote bag for Leslie Frost. Is Leslie Frost here? Okay, I will reshuffle. Frida Candido. Okay, and now let's take one more in-person question, and then we'll break, and you can feel free to come up and ask Matt or any of us.
Go ahead.
Set one of these things up with how many different people, like, so, I mean, I suspect you're just not going to vote, you know.
Yeah.
So, it literally, it is, where you did all that whole,
Yeah.
and here we go. I gotta figure this takes for.
It takes a long time to learn, but when you get good at it, it's really fast. So, you know, I've been doing this now for 10 years, I think. And so if someone emails me with some data, probably in an afternoon, I can do one of these things. It's you know, it depends on the data, it depends on the problem, it depends on the physics, but like I have all of the tools I need and I'm really good at using them. But to learn all of that takes, I mean, to learn first off just the math behind all this stuff takes a long time. And so we're slowly building these tools to make it easier and easier for anyone to use. But at the moment, it requires quite a bit of background knowledge to really get it right. So, yeah. Yeah. Okay. Thanks. I just want to say, I know they're not going to take credit themselves, but I want to thank all of the graduate students and all the people from Columbia Outreach for setting this up.
Yeah, and thank you all again for navigating the weird security system of Columbia to get here tonight. Yeah, it's really great that so many of you showed up. Hopefully we'll see some of you again in a month. Otherwise, you can stay tuned for announcements of our sidewalk astronomy or our programs in the parks or the libraries, and we'll try to keep all of you updated. So thank you again, and thank you to Matt.
Okay, I mean, I used to come here before COVID. I don't remember.